Hello everyone, welcome to video 6. This video is titled Complex Numbers and Polynomials. So to connect this to the last video was about how do we factor polynomials and find their roots. And this is actually continuing on from that because complex numbers are how we factor polynomials that don't factor completely in the real numbers. Okay. So I'm going to get started. If you like, you can pause the video and write down this agenda, and that can help you remember later on what this video contains. Okay, so before we introduce complex numbers, we're going to talk about the best that we can do when we're not using complex numbers, when we're only using the real numbers. And I'm going to start things off with a theorem here. Now, I haven't used the word theorem in class or in the videos yet. What a theorem is it's a statement in mathematics that is true. So something that is just generally true about math and the way it works. And usually I write theorem because I think it's important enough that you want to remember it on its own. So what this is saying is that any real polynomial can be factored into a product of linear and quadratic polynomials using just the real numbers. Okay, and we've seen examples of this in the last video where I took a bunch of polynomials and I showed you what their factorizations are. And this example here, I actually just stole from the end of that video. I have a degree 5 polynomial. I'm not going to read through the whole thing. But I claim that that degree 5 polynomial can be factored like this, using just the real numbers. Okay, so what that means is that I have this written as a product of 3 linear polynomials, actually, because the square means that this x plus 1 is counted twice, and 1 quadratic polynomial. And that quadratic polynomial doesn't factor anymore with just the real numbers. Okay, so if I was counting roots, I would say that this has 2 real roots, x equals 3 and x equals minus 1, where that root x equals minus 1 has multiplicity 2. So you can watch the last video if what I said didn't quite make sense. All right, however, some quadratic polynomials, like this x squared plus x plus 3, are irreducible when I'm only using the real numbers. Okay. However, there is a number system where these quadratics factor, and it's a larger number system, a number system called the complex numbers. Okay. So let's start talking about complex numbers. All right, so what is a complex number? Well, it looks like a plus bi, where the a and the b here are just regular real numbers. Okay. So I'm going to go through a few examples of this. These examples are pretty straightforward. So 2 plus 3i. That means that a here is 2 and b is 3. Similarly, 3 minus 5i works. The minus is okay. That just means that the b is minus 5. I could even put pretty weird real numbers in these things, like square root of 2 and pi. So square root of 2 plus pi I would be a perfectly good complex number, although I hope it's not something that would appear too often in a problem. All right, now there are some examples that we have to parse a little bit that still count as complex numbers. For example, if I just have a number in front of I, like 4i, that counts because I can think of that as 0 plus 4i. Now a number times I actually has a special name. These are called imaginary numbers. So if you remember that term from a previous class, that's what it means. They're just a special kind of complex number. Okay, even real numbers like 7, real numbers are also complex numbers because I can write 7 as 7 plus 0 times I. Okay, so that's why I'm saying that complex numbers are bigger than real numbers because they actually include the real numbers in them. All right, so I haven't talked about the I yet. So the important thing to know about the I is it's not really a variable. It always means square root of minus 1. Okay, now the way you think about that is when you're doing calculations or arithmetic with complex numbers, anytime you see I squared come up, you can replace that I squared with -1. And you're going to see that happen a little bit later on. Okay, so we can do all 4 operations with complex numbers, the same 4 operations that we can do with real numbers. I'm talking about addition, subtraction, multiplication, and division. They all work just as well with complex numbers. And I'm going through examples of each of these in this slide. The first 2, addition and subtraction, are pretty straightforward, I would say. As long as you're kind of careful about the parentheses. So, for example, I'm adding 2 plus 3i and 5 minus 7i here. And what I would have, the way I encourage you to think about that is to sort of group the like terms. So I'll group the 2 plus 5 and get 7, and I'll group the 3i and the minus 7i and get minus 4i. Here I can kind of treat that i like I would in x. Same thing with subtraction pretty much, although just keep in mind, just like with polynomials, I want to remember to distribute the minus. So when I see minus 5 minus 7i, that minus minus is going to end up becoming a plus. So as long as you keep that in mind, you'll do fine with subtraction. Multiplication is one step beyond this, but not too bad. So with multiplication, it's basically you want to FOIL again, just like with polynomials. So you can see me in this first step here, FOILing out this product. And here are the 4 terms I get. Now notice that I'm getting an I squared here. And remember that golden rule which says that anytime I see an I squared, I can replace that with a -1. So if I do that, if I replace this with a -1, now I have minus minus, and as you might guess, that minus minus is going to become a plus, and that's how this ends up being 31 plus I. Okay, now division, there's a trick to it, and it's a complicated enough trick that I actually wrote this one out in longhand. Okay, now first I'm going to tell you what I'm doing, and then I'm going to talk about the trick in general. So to handle this division, I'm going to first multiply top and bottom by the same thing. So I'm not changing the fraction because I'm multiplying top and bottom by the same complex number. And that complex number is 5 plus 7i. And what I've done here is I've taken the denominator and I've replaced the minus with a plus, or I've switched the minus with a plus. And I'll talk about what that means a little bit later. But if you could follow the rest of the calculation, which is just doing the multiplication that I did in the last step. So I'm multiplying what's happening in the numerator, and here's what I get. And I'm also multiplying the denominator too, and now something kind of interesting happens here. I get cross terms from FOILing out, minus 35i plus 35i, but hey, those cancel. And in fact, the denominator after the canceling doesn't have any i's at all. And that's actually what's supposed to happen. So this will simplify to minus 11 plus 29i over 74, 25 plus 49. Okay, now I can then split that up using my normal fraction rules, because I can split it up because the plus is in the numerator. And lastly, so now here you can finally see that a plus bi. It just happens to be that both the a and the b are fractions, and that's fine. There's no further way that I can simplify that. Okay, so what was the trick I used there? All right, well, the trick involves something called the complex conjugate. So every complex number has a complex conjugate, and the way to get it is to switch the plus with a minus. So the complex conjugate of a plus bi is a minus bi, and similarly, the complex conjugate of a minus bi is a plus bi. And what's the trick to dividing complex numbers? It's to multiply both the top and the bottom by the complex conjugate of the denominator. In this case, that's 5 plus 7i. So if you do that and you follow through the rest of the calculation, what always happens is that the denominator becomes a real number, and that's how you can then split up the fraction into an a plus bi. You can only split up that fraction if the denominator is a real number like that. Okay. So complex numbers are important because they can give us, or they can show us the roots to real polynomials that don't appear normally. All right, so what I claim is that quadratic polynomials that don't have real roots do have complex roots. And the easiest way to see this is just to see what happens in the quadratic formula. And you've probably already noticed this if you've been using the quadratic formula so far. So I have an example here, like 2x squared plus 3x plus 4 equals 0. Say I want to solve this. Well, it doesn't factor very easily, so I go ahead and use the quadratic formula. And what happens, just to kind of shortcut here, is that b squared minus 4ac ends up being negative 23 in this case. Now, I can't normally take the square root of minus 23, but in the complex numbers I can. So just to see what happens here, square root of minus 23 is the same thing as square root of 23 times square root of minus 1. That's because I can split up a square root under multiplication. And then that square root of minus 1, remember, is the same thing as I. Okay, so that quadratic formula already tells me that this polynomial has complex roots, and here they are. The plus and minus are the two different roots. So there's an important fact to say here, which is that for real polynomials, those complex roots always come in pairs, a plus bi and a minus bi, just like what's happening here. The a is the minus 3 over 4, the b is the square root of 23 over 4, and the two roots are a plus bi and a minus bi. And that always happens when we factor a real polynomial. And these two numbers, because they're complex conjugates, we call them conjugate pairs. So that's a word you can expect to hear in class. Okay. So that leads us to the final theorem to end things off. And this one is an important one, so important that it's been named the fundamental theorem of algebra. You can debate whether this is the most important theorem of algebra, but it certainly was historically very, very important. And the theorem is pretty simple to describe. It just says that any polynomial, if we put it in the complex numbers, then it factors completely into a product of linear polynomials. So basically, where we might not get complete factorization in the real numbers, we always get complete factorization in the complex numbers. And I'm going to return to that example from the beginning of the video. Here's my degree 5 polynomial again. Here's the factorization if I'm just using the real numbers. But that last quadratic factors over the complex numbers. And here's what it factors into. So the final result is that I have a product of linear polynomials, 5 of them in fact. Okay. So what are all of the roots of this polynomial? Well, there's the two real ones, 3 and minus 1. They're still there, but now we've added to that list two complex roots, minus 1/2 minus square root of 11 over 2i, and minus 1/2 plus square root of 11 over 2i. Notice that again, it's coming in a conjugate pair. Okay, so what is this theorem really saying, or what's one result of this theorem? It says that in the complex numbers, any polynomial has as many roots as its degree, but only if we include multiplicity. Remember, multiplicity is counting those repeated roots the number of times they appear. So this degree 5 polynomial, we can say that it has 5 roots, but only if we count the minus 1 twice, because remember that minus 1 has multiplicity 2. So as long as we count roots twice when they appear more than once, then we get to say this very nice and beautiful fact, which is that a polynomial will have as many roots as its degree. And that's the first thing that makes complex numbers such a nice number system to work with. Okay, so I'm going to end things there and remind you guys to find one question in this video that you have, either in the problem solving or in the concepts, and bring that question to class. I'd be happy to answer it there. All right, thanks everyone. Have a great rest of your day.